Lesson, we're going to look at a special case of freefall known as a horizontal projectile, where an object is launched with an initially horizontal velocity and then it falls solely under the influence of gravity. So let's take a look at what's going on. So an example of a horizontal projectile would be like an object that's launched in a horizontally directed cannon, meaning strictly in the x direction. So what we can do here is we can regard the motion of our cannonball when it's launched as a combination of two different types of motion. A gravity-free motion, in which case our object heads strictly in the horizontal direction, and a path consisting strictly of gravity, where our object falls due to the acceleration due to gravity. Okay, so the resulting combination of the x-direction motion, the gravity-free path, and the vertical motion direction results in a typically parabolic path that we see with projectiles, say whether it's a football being kicked, or a cannonball being launched, or a gunshot being launched, or a gun being fired. So here's some major features of horizontal projectiles. Since our object is initially launched in a horizontal direction, the initial vertical velocity is 0. Again, in the vertical motion, it's like we're dropping an object from rest, whereas in the horizontal direction, it's like our object is being launched with an initial horizontal velocity. So our initial vertical velocity is 0, and all our initial velocity is thus in the horizontal direction. Secondly, because we can regard the direction of motion as a combination of two different paths, a gravity-free path and a vertical motion path influenced only by gravity, we say that the horizontal motion is independent of the vertical motion, meaning that the acceleration due to gravity only affects what's happening in the vertical direction, since gravity pulls us down to the earth, and thus the acceleration due to gravity has no effect on what's happening in the horizontal direction, hence why we have a gravity-free path as one of our paths for our combination. So this gravity-free path, our horizontal direction path, is not affected by the acceleration due to gravity, since gravity only acts in the vertical direction. So the vertical direction is only affected by the acceleration due to gravity. So as a result, the horizontal motion is independent of the vertical motion, meaning that free fall and the acceleration due to gravity will only affect the vertical motion, while any motion in the horizontal direction will not have any effect on the vertical motion, and vice versa. So the last big thing we can come to is that after our cannonball is launched right here, remember we're neglecting air resistance, so we don't count air resistance. So after our cannonball is launched, there's nothing affecting the motion of our object in the horizontal direction. There's no gunpowder or anything, there's no pushing going on the cannonball in the horizontal direction after it's launched. So as a result, there's nothing influencing the motion of our cannonball in the horizontal direction. So as a result, our object has a constant horizontal velocity. We can see this by the equal spacings between the balls in the horizontal direction. Okay? So after the object is launched, nothing will influence the horizontal motion of the object because it's no longer in contact with the cannon, nor is there air resistance. So the horizontal velocity remains constant throughout the trajectory, and thus the horizontal acceleration is 0. Again, we have to remember that the horizontal velocity in the horizontal motion is not affected by what's happening in the vertical motion. So our horizontal velocity is unaffected by the acceleration due to gravity, and the acceleration due to gravity, since it's strictly in the y direction, refers to our vertical acceleration. The horizontal acceleration is independent and 0 since our horizontal velocity remains constant. Thus, we must always remember to distinguish between vertical motion and horizontal motion for a horizontal projectile. An illustration of this showing the major features is shown at right. If we launch a cannonball with initial velocity of 20 meters per second in the horizontal direction, its horizontal velocity will always remain at 20 meters per second. There's no horizontal acceleration, nor does the vertical motion affect what's happening in the horizontal direction. Now in the vertical direction, we do have an acceleration, the acceleration due to gravity since we're falling down, and this causes our object to speed up at 9.8 meters per second squared, like we can see happening right here. So our object speeds up in the vertical direction because the acceleration due to gravity affects our vertical motion, but it stays at a constant velocity in horizontal direction because the acceleration due to gravity strictly acts in the vertical direction. And thus we have no other things influencing our motion in the horizontal direction. Nothing influences our motion in the horizontal direction. Again, it kind of sounds like I'm being a dead horse, but I cannot reiterate this enough as it is a very tricky concept to look at. So now we look at solving horizontal projectile problems. So the main strategy we have is, since the x and y directions are separate, we're going to write down all our unknowns and knowns for separate x and y directions. We are not going to mix the two up, okay? And we're going to subsequently identify what the problem is asking you for you to solve. So it's just like a kinematics problem. We're going to apply kinematics to horizontal projectiles. Now, what we're going to do is determine which equations we need to use. And then if needed, we're going to switch directions to find time. Sometimes you may have to find your time to use an equation to solve for something in the x direction. In that case, what we're going to do is we switch directions to the y direction to solve for time. The idea being is that time is the same in both directions, so it serves as a bridge that connects the otherwise independent x and y directions. So if I'm trying to solve for something in x direction and I need the time, I'm going to go to my y direction to solve for my time, and vice versa. If I need to solve for something in the y direction and I don't have time, I'll move to the x direction to find time. And lastly, we go back to our original direction once we have found our time in order to solve for our unknown. This seems a little bit complicated, and it can be a little bit complicated, but it's simply a modification of kinematics. I actually shouldn't say simply, since nothing in physics is simple, but you will come to see when we get more practice with this that this extra time step is just an additional step in the process of kinematic equation solving. So let's see what this looks like in practice. Example 1 with horizontal projectiles. A cannonball is launched horizontally at a speed of 10 meters per second from a cliff at a height of 15 meters. At what distance from the cliff will the cannonball hit the ground? So the first thing we're going to do is we separate our knowns and unknowns into the x and y directions. Okay? So we know x naught is 0 meters. That's where we measure from right here. We know our initial horizontal velocity is 10 meters per second. And we know that our horizontal acceleration is 0 meters per second squared. For these horizontal projectile problems, it will not tell you your horizontal acceleration is 0. That is something you have to know as a key feature of horizontal projectiles, going back to the second slide of this PowerPoint. Now in the y direction, we know our initial height is 10 meters. We know our final height is 0 meters as we're going to end up on the ground. And we know that our initial velocity is 0 meters per second as our object in the vertical direction starts from rest. And lastly, we know that our acceleration in the vertical direction is negative g because we're still in a state of free fall here. Once our ball is kicked off the cliff, there's nothing else affecting our motion besides the influence of gravity. So we're in a state of free fall, so our vertical acceleration is negative g. So based on the information above in step 2, I identified that the best candidate to find x is the kinematic equation x equals x naught plus v naught x times t plus 1/2 axt squared. I denote ax and ay here with the subscripts x and y to clearly distinguish between the two different types of accelerations. Please note here that we cannot use vx squared equals v naught x squared plus 2ax times x minus x naught, since our acceleration in the horizontal direction, ax, is 0 meters per second squared. So as a result, we're going to have 0 times x minus x naught, which means we're going to get rid of this x minus x naught term, which is against the point because we're trying to solve for x. However, we also unfortunately do not know what time is the time that our object is in the air for. So what we do here is we're trying to solve for something in the x direction, and we need time, so we're going to go for our y direction in order to solve for the time it takes our object to reach the ground. Hence, step 3. So using the y direction, we can find time. Based on our knowns in the y direction, we see we need to use y equals y naught plus v naught y times t plus 1/2 ay times t squared. We know that our final height is 0, so y is equal to 0. We know our initial vertical velocity is 0, so we set this middle term equals 0. So we end up with 0 equals negative 1/2 gt squared, or 0 equals y naught minus 1/2 gt squared. Note that this is the same result as we get for a typical freefall problem, and again, this is expected because a horizontal projectile is a special case of freefall. In the vertical direction, we only have the influence of gravity acting, and hence this is a freefall scenario. So now we solve for our time t, and as a result of solving the subsequent equation, we get that our time t is equal to square root of 2 times y naught divided by g. So t is going to be equal to, when we plug in all our information, 2 times 15 divided by 10, and then we take the square root of that, which gives us that our object is in the air for 1.73 seconds. Now that we've found our time, we can go back finally to the x direction and find out how far our object has gone in the x direction. So in our direction, we can now use time to find x. x equals x naught plus v naught x times t plus 1/2 ax t times t squared. We know our initial position is 0. Again, we measure from the edge of the cliff. And then we know that our horizontal acceleration is 0. So as a result, we end up with x equals our initial horizontal velocity times time, or 10 meters per second, times 1.73 seconds, which tells us that our object travels 17.3 meters. And this is the main process for applying kinematics to horizontal projectiles.